So we'll start with Professor Marleen de Bruijne, who's both at the Erasmus MC in Rotterdam and the University of Copenhagen in Denmark, and she'll talk about the limitations of AI in post-processing. Thank you very much, and I'm happy to hear the talk.
So thank you, and thank you for the invitation to speak here. I hope you can all see my slides correctly. If not, let me know. So I was asked to talk about the limitations of AI in post-processing, and I want to show you some possible solutions as well. And today I want to talk about a specific type of AI, the learning-based systems, machine learning-based systems that learn from examples how to solve certain tasks. And here you just see just one successful example of deep learning in medical image analysis. So we can now, using deep learning, solve many challenging tasks as good as human observers can. The example on this slide is the segmentation of intracranial calcifications, with more classical image analysis techniques could not solve. Because it's quite a difficult problem, because the shapes of these calcifications and their location, they are difficult to predict, and also there are neighboring structures that have exactly the same intensity and sometimes appear to be touching in the CT scans. So this is just one example, and we have seen in the past few years many examples in which deep learning performs as good as or even better than humans. So this development has gone really rapidly. You see really an explosion in the number of papers talking about successful applications of AI in medical image analysis, and then specifically in radiology and pathology. But of course, I was asked to talk about the limitations. So, well, let's first look at what the users think. These are the results from a recent survey of AI use among radiologists from the American College of Radiology. But a similar survey in Europe found similar results. So what they found is that 30% of radiologists currently use AI in some form in their daily practice, and 20%, so about half in total, plan to purchase AI solutions in the next 5 years. And overall, their experience is positive. They think AI is valuable and typically has good accuracy. What you see in this plot here is that they have very low trust in autonomous AI. Well, I think that's sensible at the moment. And the main reason is that the performance is inconsistent, what they found. So there is a clear limitation of current systems. And almost all limitations of current AI systems, I would say, relate to the data that these systems were trained on. Deep learning requires a lot of representative annotated training data. So, for instance, in the famous deep learning book by Goodfellow et al., they say that as a rule of thumb, you would need at least 10 million labeled examples to exceed human performance, and at least 5,000 labeled examples to get generally acceptable performance. Well, I think this is way too pessimistic. In medical imaging, we have seen excellent results with much fewer training samples. For instance, the example that I showed you on the intracranial calcifications, it was trained just on 1,000 examples with ground truth. But we did see that we made more errors in the more rare cases, and also if we increase the training set size, results still improve. So good models require a lot of training data, and that is a problem because high quality annotated medical imaging data is difficult and expensive to obtain. So, as I mentioned, I think most current limitations are related to the training data. Often there's not enough training data, or there's not enough annotated data. Data is only partially annotated or poorly annotated. Those are quite common problems that I think most of you have already heard about. And what I want to discuss in a little bit more detail is what happens if the data is not representative enough. So what does that mean really? Well, so say for instance, if you have trained this deep learning model to segment brain tissue in brain MRI. Now, no one would really be surprised that if you feed this model a cardiac MRI, that then the result is not reliable. But what happens if you show the models different scans from slightly different scan protocols? So they can look really visually different, they can have different contrast properties, but they still show all the same tissues. And for a radiologist, it's no problem at all to judge these different scans. But for a machine learning system, often if you've trained on the kind of images that you see on the left and you apply it to any of the other protocols in this, on this slide, your results will be less good. So here you see an example of that, an MRI brain segmentation tasks. If we train the model on all MRI images, on a large data set of MRI images, and only very few of the examples were from the target protocol that we're interested in, we get a result like this, which is clearly not good enough. Now, if we had, in this case, if we had trained the model only on the examples from the target protocol that we were interested in, we would have gotten a better result, but still, a lot of the details are missing because then we would not have enough training data to get a reliable result. And there are many works, so we have done some in our group, but also many works worldwide, showing that transfer learning, also called domain adaptation approaches, can considerably improve image segmentation across imaging protocols. But let's look a little bit at a little bit more detail about this specific case. So actually, the kind of examples that we wanted to apply our segmentation to, we had seen them in the training set, but they were just rare. And this is a problem that can happen, and it's much less clear, more difficult to observe than the model completely failing if you move to a different kind of protocol. So in our deep learning models, typically we optimize a loss over all training samples. And that means that we make decisions that are good for the majority of cases. And that may mean that we may overlook minority cases. So there are some examples. So we have a risk of biased decisions, and there are some striking examples of that also outside medical imaging that I want to share with you. You've probably seen some of these in the news. This is already a little bit older. So for instance, early software for speech recognition could not understand women well because it was mostly trained on examples of the software developers themselves, which were mostly men. Also, face recognition, early face recognition did not perform well for everybody, and made sometimes very painful mistakes. And software in use to predict who was most likely to commit future crimes turned out to be strongly racially biased. Also in medical imaging, we have to be very careful on what data and what populations we train our systems. So here you see a famous example within medical imaging. In 2017, Nature published a paper showing that an AI trained to classify images of skin lesions as benign lesions or malignant skin cancer. This model, trained on more than 100,000 skin images, achieved the same accuracy as board-certified dermatologists. And this spurred a lot of discussion to what extent these results were realistic and could they be transferred to other data sets. And they found that in this case, the algorithm turned out to be more likely to interpret images with rulers as being malignant. And that is because typically, if there's a ruler, so dermatologists typically, they use the ruler when they find a lesion really suspicious. So the very clearly benign cases, they don't have a ruler. And that biases our training data in this case. So these biases may be fairly difficult to detect, may not even be related to anything directly relevant for the diagnosis in the image. So very important to remember for developers, but also for users of AI systems. AI systems may run into problems when the test data is acquired with a different scan protocol, or when the test population is different, or just when the test image is a rare case, for instance, a minority belonging to a minority group. And having a large training set helps, but it does not solve the full problem. There may still be biases. So it's very important to know your training set, know what data you can reliably predict, know what biases there could be, and understand the risks in using these systems. Another limitation that I wanted to show, which is not, well, less directly related to the data that we're training on, is the vulnerability to adversarial attacks. So we know from computer vision that neural networks can be fooled. Here's a striking example. You see here 3 different images that were all classified correctly by a deep learning system. And now if you change the images just a little bit by adding this kind of specific noise, so to our human visual systems, these images still look exactly the same, but now the model is very certain that all these images depict an ostrich. And the same, of course, not surprisingly, can happen with models trained to analyze medical images. So let's look a little bit further, a little bit closer at what this means. The principle of all adversarial attacks is that we add something to the image, a little bit of noise, but that's not random noise, it's noise that is related to the gradient of the loss with respect to the input image. And that means that attacks are best if the attacker knows the exact model parameters. If the attacker does not know the exact model parameters, they can still train a similar model, a so-called surrogate model, and attack that. So the more the attacker knows about your system and can build a reliable, a similar surrogate model, the attacker can be successful. And we have seen in other applications that attacks do transfer between models. So what is really the risk within medical imaging? We studied how vulnerable medical classification models were to adversarial attacks. And it's difficult, I think, to know what is really a realistic attack scenario in medical imaging, and that depends very much on the specific situation in which these systems are deployed. We think it's reasonable to assume that the attacker will not have complete knowledge of the model parameters, but can make an educated guess about how the model would look like based on descriptions of the model. The attacker will probably not have the exact same training data. The attacks using adversarial attack approaches are only make sense if the perturbation is small, so it can be easily observed. We've looked at 3 different application areas: detecting diabetic retinopathy, X-ray, chest X-ray abnormalities, and detecting the presence or absence of metastatic tissue in histopathology images. And here you see some of the results. So let's first look at the worst case. What you see here is the percentage of the drop in performance of our models that are attacked in different ways. So without attack, we have 100% performance, and with attacks, typically less. These are black box attacks, so models are not known exactly, and we train a surrogate model that to design the attacks. And when both architecture and the training data are the same between the model and the surrogate model, then we observe a significant drop in performance for all applications. And the drop is smaller when the training data are different. When the architectures are different, the effect is less clear. And when both architecture and training data are different, but note that the training data, the exact samples are different, but they're still a subset of the same data set, then attack models still keep around 80–90% of their original performance. So that's perhaps a more likely realistic situation where attacks do have an effect, but not as bad as we've seen before. Then we also studied the effect of pre-training on publicly available databases, in this case, ImageNet. And we can see that if both the model that we want to attack and the surrogate model use the same kind of pre-training, then the performance really drops dramatically. So actually the bar for the ophthalmology application, it's not missing, it's just the performance really dropped to 0. And the effect is slightly smaller if the architectures are different, but still quite strong. So to conclude this part, black box adversarial attacks can be successful, but much less so if the training data and the model architecture are unknown, if they are different between the model and our surrogate model. So that means actually an important topic for this specific meeting, I think, that open science also opens us to vulnerabilities in the systems. I strongly believe that for the scientific development, we should still remain open and disclose everything and share our codes. But for deployment of systems in medical practice, we may consider that it could be better to not disclose all the details of our training data and our model. Pre-training on publicly available datasets may dramatically increase model vulnerability. And that is even when the target and the surrogate's architecture are different, and even when they use different training data. And of course, this I've shown you here classification, but the segmentation models can be attacked in similar ways, although the attack may be different, more easy to verify because you can see that the results are wrong. I wanted to come back to the problems with the data and show you a possible solution, but I think we don't have time for that anymore. I'm looking at the chairs. I'm not sure exactly when we started. We started a little bit later. Maybe
you have a couple of minutes.
Okay. So these are the points that I showed you before. Possible solutions for the small dataset problem. Of course, sharing, very important. I'm sure you are discussing that a lot in this week. Federated learning, I think you're probably seeing and discussing that as well this week. So there are ways to train models on large and multi-site databases without actually sharing the data, which may make it easier for privacy issues. Crowdsourcing annotations, I don't have time to show you anything about that. Synthesizing data may help if you can't afford to collect more data or better share data. And then there's a lot of research on how to learn good models, how to learn reliable models with less data. And there's one example that I'd like to show you about that from my own group, which is on weakly labeled learning. First, what do I mean by weak labels? It's basically any kind of label that provides less information than the label that we want to predict. For instance, if the task is to segment white matter hyperintensities in this MR brain image, then strong labels would indicate for every single voxel, does this voxel belong to a white matter hyperintensity or not? And weak labels could be, there's a moderate lesion load in this image, or there are white matter hyperintensities present, or maybe the number of lesions that are visible. And here's one example. The task here was to quantify enlarged perivascular spaces which is a marker of small vessel disease and a predictor of vascular dementia and also of stroke. And these perivascular spaces, large perivascular spaces, they look like bright and elongated structures, very small structures in these T2 scans. And the problem is there are often so many, they are very small, it's hugely time consuming to annotate this manually. What is currently done in quantitative studies is a visual scoring, which typically looks at different brain regions and then counts the number of lesions in specific slices in the brain. And we trained a neural network to, based on this, just the number of lesions in specific slices, we trained a neural network to reproduce such score. And it turned out that based on this very, very limited information, the number of lesions in one slice in the image, if we train a model to predict that on a large data set, I must say we had 1,600 scans for training, we actually end up with a model that can do this prediction really well. It is similar to the inter-observer agreement. It's more consistent than within observers if you apply it longitudinally. You can see here on the top the visual scoring and below the automated scoring, the relation between detected and large perivascular spaces and age. So these relations are very, very similar. The model predicts very similar as human observers do. Well, of course, that only tells us that we found a good predictor, but we're not really sure yet whether those are really the lesions that we're interested in or something else that correlates with our outcome that we were interested in. So we also looked at the attention maps of our network, and this revealed that the network is actually focusing on the correct type of lesions. So I can't show you all the analysis that we did here, but I can assure you it's not just something that correlates well with visual scoring, but also focuses on the correct lesion, uses information from the entire region, not just a single slice, can actually discriminate between different types of lesions, even though it was not really trained to do so. And we think this is a very promising way of training models that could replace visual assessment in large studies. And it, perhaps more excitingly, it could even be better than visual assessment because we are using the full 3D information and could in principle also use this to quantify shape, volume of the lesions. That is all I wanted to show today. Thank you for your attention, and I'd be happy to answer any questions.
Yeah, thanks for that very nice presentation. And from my side, sorry for joining late. I also had a little bit trouble to really update the Zoom account on this computer. Anyways, I saw that there are a lot of participants who also joined a little bit late and now probably need some time to post some questions. I think there's now one question coming in. It's actually the only one. Mr. Bruijne, I just wanna read it, but I think if you open the Q&A panel, you can also have a look at it. So the question is, could you comment what could be the reason that makes pre-training on public data set increase the vulnerability? And if we have very limited data, what can we do to evaluate this issue? For example, for image reconstruction application.
Yeah, so we saw this. So we compared different initializations of the model. So that's pre-training with ImageNet or random initializations. And we saw that the most successful attacks, they used the same initialization strategy as the original model, and that in itself is surprising. So also a randomly initialized model can better be attacked by a randomly initialized surrogate. So what this pre-training on ImageNet does is, it's a very large data set. So it's likely that because there are so many examples, there's so much information to train the model on, we are likely to end up with a more similar model if we have a larger training set. And that is, I think, why specifically pre-training on ImageNet really opens us up to vulnerability, knowing that many people pre-train on ImageNet and the attacker may guess this. A possible solution is to maybe not, for systems to deploy in clinical practice, maybe not provide too much information on pre-training. So if pre-training can be helpful, but you can also use, for instance, self-supervised learning. There are so many different ways of training good models that perhaps taking a slightly less obvious choice is better. I hope that answers your question.
I think so, yes. So to do it in a very simplistic way, would you agree to the saying that the more you know about the network you're trying to attack, the easier the attack will be?
Yes, exactly. But I think it's also because the ImageNet is a very large data set that the effect is even stronger in this case. But yes, attacks, white box attacks, where you know the exact model, the exact parameters, they are much more successful. And the closer you get to a white box situation, the more dangerous it gets.